In my previous video on binary trees, we stopped at this slide. And I said that while binary trees have lots of uses, if one of those uses is to search the binary tree, then we want it to have two additional properties. One of those is called the binary search tree property, which then makes it a binary search tree, and the other is balance. If we're trying to search a tree that doesn't have those two properties, well then a binary tree is really not very useful. So let's look at some pictures and see how all this works out. So let's start with balance. What is that? Balance means that your tree, as much as possible, has sort of a triangular shape to it. Maybe I have 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes, and this is what I have. Well, I can't completely balance it without adding additional nodes, but this is sort of triangular in shape. So I would say this is balanced or close to it. But if instead I got something that looks like this, I wouldn't call that balanced. And so why is that an issue? Well, it depends on what we're doing. If we want to maintain balance, and if I don't care about other things necessarily, if I add new nodes, well, I could just do this. And now I still have balance. But we'll see that when we're talking about a binary search tree, having balance is going to be somewhat critical for the binary search property to be of use to us. So now let's talk about the binary search property. So the binary search property says that the nodes to the left of a parent node have values less than or equal to the parent node. And nodes to the right of the parent node have values greater than the parent node. Now sometimes you'll see it without the equality. It really depends on what you're doing and whether or not you can have duplicates. If you can't have duplicates, well then you don't need to worry about equality, and it simply becomes less than and greater than. But what does this mean? Well, let's say I have these numbers here and I have this tree. And I'm going to make it balanced, although they're really independent things. The binary search property and a balanced tree are two different things, but we would like to have both. So let's say we have this 4, 2, 1, 3, 6, 5, and 7. So now if I look at 4, we can see that every node to the left, not just the child of 4, but his children and their children and so forth, have values that are less than or equal to 4. Because 1, 2, and 3 are all less than 4. And everything to the right of 4 is greater than 4. So we move down a level. What about 2? Well, everything to the left of 2 is less than or equal to 2. Everything to the right of 2 is greater than. For 6, 5 is less than or equal to 6. 7 is greater than. And so this has this property. All right. So how is that helpful to us? Let's look at a tree and do some calculations. So let's go back and say we have this tree here. And we'll put those numbers back in here. Right. So we have a depth to the tree, which is a measure of how many levels we have. Right. And let's look at total nodes. So let's say we have depth and total nodes to this point. So this is level 1, this is depth 2, this is depth 3. Each of these could have nodes. So it's level 4. So how many nodes do we have here? Well, at this point, if we stop here, we only have 1. If we come down a level, then we have 1, 2, 3. If we add an additional level, that's 4 more, so 4 and 3 is 7. Here's 8 more, 8 and 7 is 15. What's the relationship here? Well, this right here is equal to the level, or the depth, which is 1, minus 1. That's 2 minus 1 is 1. 2 squared is 4, minus 1 is 3. 2 cubed minus 1 is 7. 2 to the 4th is 16, minus 1 is 15. And it continues that way. So how's that useful? Well, imagine we want to store 1,000,000 things, and we have not only the binary search property, but we also have a balance tree. Okay, so 2 to the 20th is about 1,000,000. It's actually a little bit more, because 2 to the 20th is equal to the 10th times 2 to the 10th, which is 1,024 times 1,024. So that's actually greater than 1,000,000. So based upon what I just saw here, this means that if I have balance to what I have, well, then my tree has at most 20 levels. So level 1, level 2, down to 20. Because I have this balance. So how's that useful? Well, let's say I need to search for something. Now, if I'm searching here, and I have the binary search property, and once again, the balance part has to do with performance. It doesn't affect how I'm going to operate. But let's say I'm searching for the number 7, and we'll stick to our original tree right here. Well, I'm going to ask the question here, is this equal to 7? Since the answer is no, I know it cannot be on the left, which means I just ruled out basically half the tree. So I come down to this level and say, well, is that equal to 7? The answer is also no. So now I rule out the other quarter that's right here and work down and say, well, there's 7. So if I had 1,000,000 nodes, approximately, and the same type of thing applied, when I go down one of the sides initially, so I check with the first node, and if that's not what I need, I either go left or I go right. By making that jump to the next level, I've eliminated basically 500,000 nodes. And then say if I'm going down this side and I end up here, well, now I've just eliminated another 250,000 and so forth. So what's the worst case scenario if it's balanced? Well, the worst case scenario is I work my way down and I get all the way to the bottom. Well, that's only level 20. So I compared once at level 1, compared a second time at level 2, compared a third time at level 3. So it means at most I had 20 comparisons within 1,000,000 things. That's why it's a good thing to have both balance and the binary search property. If I don't have the binary search property and these are in some apparently random order, I might have to look at all 1,000,000 things to see if what I'm looking for is there. So why is balance important? Well, let's imagine I have this tree at the top and I construct it like this. So let's say the way I get the numbers is in numerical order. So I get 1 and put it here, and then I get 2. So it goes over here to maintain the binary search tree property. I get 3, it goes here. 4, 5, 6, and 7. Well, this does maintain the binary search property. So this is a binary search tree, but it's not balanced. So for all intents and purposes, it's a linked list. Except it took more work to construct this than it does an actual linked list. So this doesn't benefit me at all. So that's why I want to have this plus balance. Now, if you're trying to maintain the binary search property and maintain a balanced tree, that turns out to be very challenging. So I'm not really going to go into this because it's really beyond the scope of what I want to teach here. And it's really something you should see in a data structures course. But let's see what the problem is. Well, let's say I get these numbers in this order. So I get 1 initially, so here's my tree. Then I get 2, so at the next level, I have this. Well, I can't make it any more balanced than this, so that's just the way it is. But then I add 3. Well, now I have enough nodes that I can make this balance. So instead, this needs to be shuffled around to that, with 2 as the root, and now it's balanced. And so as I add additional nodes, you can shuffle things around to where you could actually get this eventually. But that takes a lot of work, and then you have to do the same type of operation if you want to remove nodes. If I had this right here, or if I had this right here and say I remove the 6, the 5, and the 7, well then I need to do some shuffling around so that way 4 is no longer the root. But let's look at how you can use the binary search property in your tree. So we're going to have a function that does the insertions, and it's going to have a return type of void. We'll say insert. It receives the address of a pointer to a struct node. So struct node star, we'll call this root, and then the number n that I want to insert. Let's look at how this works first. So I'm going to deliberately create a balanced tree just because it makes it easier to see things, and then also to demonstrate an application of binary search trees as well. But let's look at what the process is. So I receive the numbers in this order, and this will actually force this to be a balanced binary search tree. So we have 4, then we get 2, then I'm going to get 6, and technically I do have some flexibility in the order in which I add these. Then I'm going to say 1 and 3 and 5 and 7. So there are other orderings of this that would still give me the same tree. All right? So what happens initially? We'll have root. I'm going to have 4 and have these stubs. All right? So then I want to add 2. So what do? Well, I come here and I need to figure out what the relationship is. So I know that 2 belongs on this side, but I need to ask a follow-up question. Do I automatically just say node 4, its left child, has this node with 2 in it or not? Well, it depends. If this is null, then I know I can just add this node here. So I do that. So I have 2. And then I get 6. I'm going to put it over here to get more room. And same type of thing applies. 6 is greater than 4, so it goes over here. So now we see what I was just pointing out is that now if I get 1, I say 1 is less than 4. But if I just say basically, this doesn't really make sense, but to be clear which node I'm talking about, if I say 4 left equals new node, then I just lost the 2. I'm putting the 1 there, and I no longer know where the 2 node is at because it still exists in memory. So instead, I say since this is not null, I want to move down to 2 and ask the same question. What's the relationship of 1 to 2? It belongs on the left of 2. And since now the left child of 2 is null, then I can safely attach this node. I get 3. That's less than or equal to 4. But this is not null, so I need to move down a level. 3 is greater than 2. Is the right child of 2 equal null? Yes. So I can attach 3 right here. Get 5. That's greater than 4. Is the right child of 4 null? No. So I need to move down a level. So I come to here. Is 5 less than 6? Yes. Is the left child of 6 equal to null? Yes. So I can attach 5 there. Get 7. Is that less than or equal to 4? No. So it's greater than. So I move down, or I move over to here. Does it attach to the right-hand side? No. So I move down a level. What's the relationship of 7 to 6? It's greater than. Is the left child of 6, or excuse me, the right child of 6 null? Yes. So I can attach the node there, and I'm done. So that's the algorithmic process. That's the step-by-step process that I need to use when writing my code. So that's what I'm going to do. So we're going to get here. So we're going to do this. So I'm going to build the original root this way, because I know that will only be the thing that's there. And then I'm going to say insert root. And I'm going to give it the 2, the 6. I'm doing the order that I just wrote down. Right? So let's look at this. So my structure definition has D as the number that I'm storing. So if n is less than or equal to root D, then I need to go left. And I'll put a comment saying that. Go left. Right? Else, go right. That's what this will be. Right? So I know which way I need to go. Now I need to make the decision. Can I allocate memory here and assign the value, or do I have to keep going? So now I say if, because I'm on the left-hand side, if root left is null, then I can attach the new node to this. So root left is equal to add node, the number n that I was given. Otherwise, I need to keep searching. And that will be insert again, but we pass the address to root left and the number n. I'm going to take these 4 lines, and everywhere it says left, change it to right. So I think that should be it. I'll clean that up a little bit. So let's see what happens. So it did run. Did it build what I need? Well, let's see what the ordering should be. So we come back to my tree, and this gives more practice with the traversals. So pre-order. I go in more detail in my other binary tree video, so look at that if you're not sure. So it's going to be 4, 2, 1, 3, 6, 5, and 7. And actually I can just copy it off the screen since I have that in order. Sorry. So it's going to be 1, 2, 3, 4, 5, 6, 7, and then post order. 1, 3, 2, 5, 7, 6, 4. Let's look at this while we're here. Notice that's in order. That's not a coincidence. If you have the binary search tree property and use in order traversal, even if it's not balanced, it will print these in order. And so one of the applications actually is to print things back out in a ascending or descending order depending on which way you process a tree. So do these match up with the tree that we wanted to construct? Well, remember pre-order says you process a node when you get there. So 4, use it. Use the 2. Use the 1. Come back to here. Use the 3. Return to here. Return to here. Use the 6. Use the 5. Come back to here. Use the 7. Yep, that's right. In order. Says use the node as you pass back through it. So get to 4, go left. Get to 2, go left. Get to 1, go left. Come back. As I pass through, I print the 1. Come over here, come back. As I return to the 2 and pass through it, I print the 2. As I'm going right, come here, go left. As I'm passing back through the 3, print it. Return to here. As I'm passing through the 4, I print it. Get to 6, go left. 5, go left. As I return and pass through, I print the 5. Return. As I pass through the 6, print it. Print the 7, that's right. What about post order? That says you deal with all the child nodes before you deal with the parent. So 4 has left and right children. So come to 2, it has left and right children. 1 has left and right stubs. So deal with 1, that's right here. Now deal with the right child of 2, that's the 3 right there. Now we can use the 2. Return to 4, come to 6. Deal with this children, 5 and 7. Now I can use the 6. And finally we can use the 4. So all those are correct for this tree, which also means that since all 3 of these match this picture, this has to also be the correct picture for what I have. right? So that was the way to insert nodes. But if I'd given this to my algorithm, it would have produced this. Which still meets the binary search tree property, but it's no longer balanced because balancing is a much more challenging process and takes a lot more work, right? But even then, if I printed this using in order, it's going to print 1, go left, come back to 1, go right, hit the 2, print the 2, go left, come back to 2, and so forth. So it still would give me the in order traversal output here, which is sorted. All right.